From binding paper together to helping us traverse Mars, nitinol's unique properties make it revolutionary in many fields. Today we will dive into and uncover the physics that sets nitinol apart from other materials. To understand some of these properties and the significance they pose, we must first look a little closer. Well, a lot closer. You may have figured from the name that nitinol is an alloy comprised of titanium and nickel atoms. These are present in roughly equal proportions, although they may be varied to alter some of its features. At first glance, it seems just like any other alloy. What separates it from the other alloys, however, is how it reacts when being deformed. Here is a close-up shot of nitinol being bent. Although deformed substantially, the bonds that hold the atoms together are intact and have now formed a rhombus shape. However, when we subject nitinol to heat, it returns back to its original shape. To compare, let's look at a different alloy being deformed. Here is brass, an alloy of copper and zinc, being bent. As you can see, brass remained permanently deformed, and added heat and pressure caused the bonds to break. The reason that nitinol was able to return to its original shape without any broken bonds is specific to the unique transformation process it undergoes. More specifically, diffusionless transformation, also known as Martensitic transformation. Formally, this can be defined as the change in crystal structure of a material, whilst preserving atomic relationships at various loads. In other words, this means that the materials that undergo this type of transformation observe a lot of change at the crystal level, but are preserved at the atomic level. This gives nitinol a memory of sorts of its original shape. This is due to science that I cannot wrap my head around despite countless attempts, so instead I will demonstrate the effect graphically. This will be a comparison of Young's modulus at different states. The first state in a Martensitic transformation is known as the austenite state. This is the state that nitinol finds itself dormant in, and is not too dissimilar from many other materials. This is also known as the parent phase. As you can observe from the shape of the graph, the austenite phase seems to be incredibly elastic, with every load up to its fracture point being able to return to the original shape as it is unloaded. The second state in Martensitic transformation is known as the Martensite state, unsurprisingly. This is a state in which nitinol undergoes change to its structure, and is not found often in. This is also known as the daughter phase. As you can observe from the shape of this graph, Martensitic nitinol now plastically deforms up to its fracture point, and when unloaded has a different shape to the one it began with. These two graphs are inherently linked, with the link being the type of stress applied to nitinol. This can be mechanical, where a large load is placed upon nitinol, making it transition between these states. The more common one, however, is heat. To go from austenite to martensite, nitinol has to be cooled. To go back to martensite from austenite, nitinol has to be heated. This compound graph demonstrates the relationship between both states and provides reason behind the properties nitinol possesses. Now that you, hopefully, understand the process of Martensitic transformation, we can begin to look at some of the features that nitinol has as a result of this. Firstly, we can look at general chemical properties. It has a density of 6.45 grams per cubic centimeters. Compared to other metals, nitinol is relatively lightweight, and the larger space between atoms allows the individual grains to fluctuate more. It has a melting point of 1300 degrees Celsius. This, again, is much lower than the other metals, which explains the quick transformations under relatively low temperatures. It has a yield strength of 195 to 690 megapascals at the austenite state, meaning a significant force is required to plastically deform it, as shown previously, but a much lower yield strength of 70 to 140 megapascals at the martensite state. You may be wondering, how is nitinol made? Primarily, nitinol is manufactured in the process known as vacuum arc remelting. This involves placing the relevant alloy ingots in a metallurgical vacuum, and using high DC currents to arc between the ingots until they melt together to form nitinol. The temperature is extensively controlled via the intricate cooling system surrounding the crucible. Now, let's look at the main uses of nitinol. One major use of nitinol is in the production of stents. When arteries get clogged with fat, it becomes increasingly difficult for blood to flow properly, and can lead to a number of dangerous health implications, such as a high blood pressure. Stents are small entryways that compress the fat and allow the blood to flow unrestricted. To solve this, nitinol is inserted in its compact state around a balloon via a string, and the string and the balloon can then be removed. The nitinol in the stent will be trained to expand at around 37 degrees Celsius, the average temperature of the human body. This means that it can easily be inserted and then fixed in place automatically. The second and final application I will talk about is potentially the most interesting: rover wheels. A problem that all space agencies face when tasked with designing an extraplanetary rover is effectively creating wheels. They will be subject to incredibly rough terrain, and must be made out of metal to avoid popping or easily falling apart. However, the malleability of metal makes it subject to a lot of irreparable damage and deformation. To combat this, nitinol is being considered in the manufacture of rover wheels. This involves braiding wires of nitinol in a chainmail-like fashion to create a wheel. Not only will this wheel be able to repair itself, but its super elasticity allows it to bend over more complex terrain. Well, that's about everything I could find out regarding nitinol. I will now conclude by listing all of my references with extensive information. Thank you.